LiDAR is an acronym derived from the phrase light detection and ranging. It is an active remote sensing technique that uses laser scanning to directly collect three-dimensional data for mapping purposes. The presentation explains the principles of laser scanning, introduces different LiDAR systems, and discusses basic LiDAR data collection procedures. This is the second of 4 RLOs developed on LiDAR remote sensing. 3 related RLOs that cover laser fundamentals, data analysis techniques, and applications are also available. A rotating or oscillating mirror similar to the first image on the left can transform a laser range profiler into a laser scanner by enabling data capture in an additional dimension not captured by the profiler. For an upright-oriented scanner, the scanning mechanism creates a terrain profile in the vertical plane. If the scanner is on a fixed platform, horizontal rotation of the sensor is necessary to capture the entire area. As shown in the middle figure, the entire terrain area is simply a series of vertical terrain profiles separated by a horizontal angular step. The image on the right is an example of a terrestrial laser scanner. The laser is emitted from behind the blue glass after reflecting off the rotating mirror. This mirror enables the scanner to collect the vertical terrain profile. The sensor uses a rotating head behind the black band to create the incremental horizontal angular steps necessary to capture the entire terrain area. Airborne scanning utilizes the forward motion of the airplane to create separation between the terrain profiles. Thus, the scanning mechanism's primary objective is to create the cross-track profiles as shown in the figure. LiDAR scanning manufacturers employ different scanning techniques depending on the rotating or oscillating mechanism used. The figures show the major airborne laser scanning patterns, including zigzag, linear, and nutating. Each LiDAR system manufacturer uses slightly different terminology for the various laser scanning characteristics. After defining the major terms, we'll look at 2 examples of LiDAR acquisition software. One for the airborne case and one for the terrestrial case. The term pulse frequency refers to the number of pulses emitted from a time-of-flight LiDAR sensor. Systems have a broad variation in the PRF ranging from 10,000 to 800,000 pulses per second. The scan rate is the number of scan lines per second. Changing the scan rate will change the density of the points along each scan line. The scan angle, phi, is the angle between the laser pulse line and the reference line. In the airborne case, the reference line is usually the nadir line from the aircraft directly downward to the ground as shown in the graphic. The scan angle range, theta, is the maximum angle the sensor moves in a scan line. Maintaining a given altitude and changing the scan angle range will affect the size of the swath width on the ground. Terrestrial scanners typically have a greater scan angle range than airborne scanners. 2 terms associated with stationary terrestrial scanning are the angular step width and the horizontal scan range. The angular step width, shown as delta in the graphic, is a term used to define the incremental horizontal angle between 2 consecutive scan lines. On a moving platform such as an aircraft, the aircraft velocity dictates the angular difference between 2 scan lines. Similarly, the horizontal scan range indicates the horizontal range of motion for the sensor head on a given terrestrial scan. The last 2 terms define the resolution of the data at a fixed distance from the sensor. Posting, denoted by D in the graphic, is the distance between 2 consecutive laser footprints in a scan line. Point spacing between scan lines, denoted by P in the graphic, refers to the distance between 2 consecutive laser scan lines. The graphic shows LiDAR flight acquisition settings for a topographic survey of a biological station from 2006. The gray parameters are predetermined by the flight operators. The cyan parameters are calculated from the given gray flight parameters. We'll quickly walk through this example to show how these LiDAR settings are calculated. First, please note that the calculated number of passes is determined by the area being surveyed, which is not shown in the graphic. Given that the sensor operates at 600 meters above the ground level and has a scan angle of plus or minus 18 degrees, we can calculate the swath width of 389.9 meters using simple trigonometry. The swath width is needed to determine the cross-track point spacing or cross-track resolution per this manufacturer's software. The scan frequency for this particular sensor counts a back-and-forth zigzag scan as one iteration. Thus, we have to multiply the scan frequency by 2 to calculate the number of scan lines per second. With 56 scan lines and 33,333 pulses per second, the number of points per scan line can be derived. Dividing the swath width by the number of points per scan line will give us the cross-track resolution of 1 point every 0.655 meters. The down-track resolution or average point spacing between lines of 0.893 meters is calculated by dividing the 50 meters per second velocity of the aircraft by the 56 scan lines per second. The desired resolution of 0.774 meters is a simple average of the cross-track and down-track resolutions. Most airborne LiDAR users want to know the average LiDAR points per square meter on the ground. We calculate this by inversing the squared desired resolution. This survey has approximately 1.7 points per square meter. Having discussed LiDAR sensors and laser scanning characteristics, a holistic discussion of the LiDAR system is necessary. LiDAR systems incorporate the Gyro Referencing component of the laser scanning process as well. Gyro Referencing is the determination of the location, orientation, and timing of an event in space. This process provides the LiDAR data with the geographic positional data necessary for mapping the subject area. The graphic depicts the airborne segment of an airborne LiDAR system, or ALS for short. The airborne platform houses both the LiDAR sensor and the position and orientation system, or POS for short. An inertial measurement unit, or IMU, consisting of gyroscopes and accelerometers measures the attitude and acceleration of the aircraft along 3 orthogonal axes. This inertial data is combined with global positioning system data to provide the raw georeferencing solution. To synchronize the LiDAR and POS data, the precise GPS time is used to timestamp the laser scanning data. The ground segment consists of GPS reference stations used in post-processing the airborne GPS data with GPS data of known control points. The post-processed georeferencing solution is then applied to the LiDAR scan data. The resultant product is a registered LiDAR point cloud. The LiDAR processing steps are explained further in the third RLO, LiDAR Data Analysis. Airborne LiDAR systems are further classified by the airborne platform, either fixed wing or rotary wing. Wide area LiDAR mapping is predominantly performed by fixed wing aircraft, as shown to the left, while corridor mapping is typically performed by rotary wing aircraft, as shown on the right image. Wide area LiDAR mapping is flown at higher altitudes with wider swath widths, lower ground point densities, and typically lower accuracies relative to the lower altitude corridor mapping performed in helicopters. Here are a few examples of airborne LiDAR system installations in fixed-wing aircraft. These images show the size of both the ALS sensor heads and the electronics rack necessary for powering and operating the systems. Terrestrial LiDAR systems, or TLS for short, have traditionally used stationary platforms, such as tripods. LiDAR targets shown in the lower left-hand image are scanned from multiple scan setups and used for registering and georeferencing individual scans into a unified set of LiDAR points called a point cloud. The image on the right shows the spacing and number of targets needed to perform laser scanning work that satisfies the California Department of Transportation's technical specifications. In this schematic, the TLS setup must be approximately equidistant between two targets less than 500 feet apart with a total of at least 4 control point targets per setup. The shaded boxes indicate the overlapping areas that will be imaged by adjacent scan setups. For each setup, it is essential to have independent validation points denoted by X's that can be used for quality assurance purposes. As inertial navigation technology has improved, TLS have been integrated onto mobile platforms such as vans, trucks, and boats. These non-stationary systems are referred to as Mobile Terrestrial LiDAR Systems, or MTLS for short. Both of the figures show schematics of systems integrating multiple scanners with positioning and orientation sensors. MTLS use LiDAR scan targets and pause sensors similar to ALS for registration and georeferencing the collected scan data. Similar to the California Department of Transportation's technical specifications for stationary TLS, the department has provided users with minimal technical specifications for operating mobile TLS. The bottom graphic shows the spacing and number of targets needed to perform mobile laser scanning work that satisfies Type A survey applications. The hatched area in the middle of the roadway shows the overlap between the two passes of the MTLS. Control points and validation points are used along both sides of the roadway at distances not exceeding 1,500 and 500 feet respectively for local transformation and data quality checking procedures. TLS and MTLS can provide greater point densities and higher accuracies than ALS but cannot cover the same spatial extent as ALS nearly as efficiently. Further, TLS and MTLS data can provide oblique data acquisition of building facades more effectively than ALS due to the orientation and location of the terrestrial scanners near ground level. Applications of these LiDAR systems will be covered in greater depth in the fourth RLO in this series. This RLO presentation provided information on basic characteristics of laser scanning. Laser scanners were then integrated as one component of a larger LiDAR system classified by the operation platform. A discussion of components and basic data collection procedures from both airborne and terrestrial LiDAR systems concluded this presentation. We conclude this presentation with a list of further reading on LiDAR principles.